Good morning, good afternoon, everyone. It's my pleasure to be here today to talk to you about a lot of the cool new features that we have in our latest release of Abaqus. Try to get my page down button to work here. There we go. So the agenda really has three key parts. First, I'm going to spend some time talking about sequential workflows. Done some very nice new developments in that area that I think will be of interest to most of you. The majority of the presentation today is going to be focused on select Abaqus enhancements. As always, there's so many that we can't squeeze them all into one session. So just a heads-up reminder that the release notes, please consult your release notes for a comprehensive list of everything that's new. I'd also like to take this opportunity just to let everyone know that, in recent years we've moved somewhat away from an annual new one release every year to more of a continuous development mode. So many of the enhancements that I'm going to talk about today were actually sprinkled in over the previous year in our fixed pack releases of the Abaqus 2020 release, and then they obviously accumulate into the 2020 release. So some of these things are available in previous releases as well. And then the last topic I'd like to talk about is material calibration and a really nice new application that we have that provides access to cloud computing. So with that, let's jump right into it. So first, the definition of sequential workflow. And what we mean by that is, any workflow where output from an upstream simulation or simulations, as the case may be, is used as an input to a downstream simulation or simulations potentially. And there's some examples shown here on the screen. Thermal stress is perhaps one of the more common, where we do a heat transfer simulation and then feed those results into a downstream structural simulation. Some other examples on the top right: assembly preloading, or some of you may be familiar with what we call import. The idea of preloading some parts or sub-assembly, and then we assemble those into yet a larger assembly so that the system level simulation can take into account things like preloads and bolt tensions and all that kind of stuff. Yet another example is submodeling, where we take a global model, typically coarse mesh, suitable for assessing the global response, and then we zoom in and do a submodel, refined mesh, more detailed, of a local region of interest. And last, another example that fits our definition here is material calibration. So here, typically we take test data and then perform some type of simulation to come up with constitutive properties that can be used as inputs to downstream simulations. So just a survey of select, and certainly not comprehensive, types of sequential workflows. These tend to be very high value workflows. They have high fidelity and provide very valuable results that can be used to minimize testing and so forth, and provide more robust designs. However, if it was only that easy, it would be great, but it's typically not, because in practice, executing these workflows can be, let's say, a little painful for the end users. Here's a typical scenario. Here we're going to look at structural analysis of injection molded parts. These types of components are everywhere. It's autos, mobile devices, consumer products, you name it, they're everywhere. Typical scenario starts with somebody doing a design in CAD. That's over here on the left. That CAD then is thrown over to an injection molding specialist using another package. So we're going to import that CAD geometry and do some cleanup, et cetera, and design the molding process. Parallel to that, or even sequential really, is we're going to do a structural simulation. So again, somebody has to import the CAD into yet another package, clean it up, et cetera. And then oftentimes what we're going to do is take the results from the molding simulation that has fiber orientations and maybe material properties, and map those into the structural simulation, oftentimes done with yet another tool or maybe in-house scripts and so forth, and then ultimately we get to the structural simulation. You can see that, typically these are transferred, the data is transferred via files and so forth. Of course, when the part design changes, okay, everything we did downstream, or at least in many cases, most of everything needs to be redone, re-import the CAD, rebuild your model, etc., etc. So it tends to be a very painful process. Multiple tools, multiple data formats and translations. Since there's different tools from different vendors, they have different versioning schedules and maybe don't always work together. And as I mentioned already, non-associative. So when something changes in the source design, it doesn't propagate as cleanly down through the rest of the process as it could. So a little pain there involved. I'm sure we're all familiar with this to various degrees or another, but we do it, and we found a way to make it work because there's enough value there to justify that extra pain. But what I'm here to say now is that it doesn't have to be this way. I'd like to spend a few moments just talking about how with our Abaqus solver and 3D experience we're working to eliminate that pain. So what we're showing on the screen here, and I'll start on the right, is the 3D experience platform and its applications. So the first point is that we have applications spanning the whole range. Again, I'm sticking with the injection molding example. So our CAD tool tailored specifically towards plastic parts. We have our structural simulation applications, plastic injection molding applications, and a material calibration application. I'm going to talk about that a little bit later in more detail. What's important here is that, first of all, they share common user experiences. So if you know one, it's easy to learn the others. And perhaps most importantly, they share a common data model. All of the data is managed and shared within the platform, and there's relationships between those. So I'll try to explain what these arrows mean. First we have the CAD design up at top. That typically drives everything downstream. And then the arrows are showing associativity or data flows, as the case when you can think about it both ways. So here, the CAD design flows into the plastic simulation. So the CAD knows that it has a plastic simulation associated with it. Likewise, the plastic simulation knows which CAD it came from. Similarly, for a structural simulation, the same can be said. So when the CAD design is outdated, the plastic simulation automatically knows about it, and the structural simulation automatically knows about it. Similarly, since the structural simulation is downstream from the plastic simulation, they also know about each other. So if the plastic simulation changes, the structural simulation knows it is now out of date and can be updated. So the analogy I like to draw here is if you think about feature-based or parametric CAD, where you create your base feature, you create your other features, holes and fillets and so forth. So this is sort of like that same concept. You change the base feature and everything downstream updates automatically. So that's really what the extra value is that is being brought to the table by what we're doing with our 3D experience platform. Okay, so now we'll talk a little bit about what we're doing in Abaqus to help enable some of these workflows. And in particular, this is a capability we refer to as external field mapping. If you've been using Abaqus for a while, there's a number of different capabilities built into Abaqus that allow mapping results from one simulation to the other. Submodel, mapping temperatures and so forth. Typically, or these have been developed over time independently. The user interfaces may be a little different and so forth. Paradigms a little different. So what we've done is, we reached a point where we said, okay, it's time to step back, recognize the commonalities, and develop a generalized capability to apply distributions, material properties, et cetera, forth, loads, initial conditions, boundary conditions imported from external field, right? And that's what this slide is really all about. And if we look at this timeline here, I'm just trying to show the different parts of a simulation where this mapping applies. So this is a time history, if you will, of the downstream simulation. It starts, it ends, and then there's some time incrementation that may not be uniform, so there's delta t's being had. So if we go back prior to the start, one of the uses for external field mapping is property distribution. So in the case of this injection molding thing, I'm mapping fiber orientations, right? But it could be composite properties, it could be thicknesses from a stamping simulation, many other possibilities of really model data or material properties and so forth that can be mapped on before the start of the simulation. Then we can map on initial conditions and boundary conditions, so maybe an initial temperature or initial plastic strains or something like that. And then the transient load mapping, as we march through time, we read data from the upstream simulation, perform all the interpolation and mapping from dissimilar meshes, and also time interpolation, because there's no guarantee that the time histories of these simulations map up. So this mapping is performed, at runtime as the simulation proceeds. You can see some of the key features listed here. Mapping of nodes, elements, centroids, integration points, time interpolation automatically performed. And then a listing here of some of the more common target fields that we use for mapping: displacement, velocity, temperatures, electrical potentials, predefined fields, etc. So pretty broad coverage there of the different types of fields that are supported. So what I'd like to do now is play a little video actually that shows another example of sequential workflows. Here it's the submodeling workflow. So this is just a description of how the workflow proceeds, and the animation, which I'm going to play on the next slide, it really covers that workflow. So we'll start this up. So we start by looking at the global results here. It's been a fairly coarse mesh typically. Like I said, we're going to try to capture the global response adequately, but it does provide enough resolution for us to see there is a region there that might be worth a little more review. So what do? We generate a submodel. Here it's done with the CAD. This is different from what the typical process, because this is all being captured as a feature. So you can see that cut plane is being captured as a feature, linked right back to the global model automatically. So it will regenerate. So we create our mesh, more refined mesh here, and so forth. Define some of the submodel attributes, the material properties, and so forth. We're already mapped automatically. Today, in the current implementation, loads and boundary conditions are redefined. That's something we're going to fix in the very near future, where we'll map all of these features directly onto the submodel, because there's no need to redefine them since they're already there. Here we're seeing the submodel boundary conditions being applied. So this is where the results from the global model are read from and then applied as prescribed boundary conditions to the submodel. And then that's pretty much it. We're ready to run the simulation. It runs, and then view and post-process results as normal. So the key point here is that it's all associative and regenerative. So when the global model changes, all of these operations you just saw performed were captured and can be re-executed with little, if any, user interaction. Okay, so with that, I'd like to switch gears and spend really the bulk of the rest of our time covering select Abaqus enhancements. And the first handful here are going to be primarily related to Abaqus Explicit. The first is improved contact resolution for foams. So if you have foams, typically they have a stiffening behavior. They start out relatively soft and then they stiffen up. And what we've found, especially in extreme cases where the foam gets really stiff, is that can have impacts on the contact enforcement and the way penalties are chosen. So this was an enhancement driven by many customers who have these kinds of workflows to revisit the contact stiffening, or the way contact penalties are chosen, I should say, to better enforce the contact behavior. So this is just an example. This is kind of a really extreme case because we get well up into this stiffening part of the foam behavior curve where these problems become most prevalent. You can see the previous implementation and then the new implementation, which provides much more uniform enforcement of the contact behavior. You can also see there's some penetrations there. Again, as I mentioned, this is a very, very extreme case where it became stiff, and if that's and there's ways to increase the scale, the penalty stiffness for these types of applications to further improve that contact resolution. Another area of improvement is with the edge-to-edge contact performance. As you might recall, we introduced the so-called dynamic feature edge criteria in Abaqus 2018, which was much faster than enabling all edges in the model, but still, considerably more expensive computationally than the default of only considering the perimeter edges. And just to make this a little more concrete, here's an example of where the default of perimeter edges, which in this case would just be the outside boundary of this little rectangle piece here. That would be the default. As it accelerates and is going to impact this other part, it develops a fold. And you can see, if we only consider the perimeter edges and not this feature edge that evolves during the simulation, we can't capture that contact correctly. So with the evolving feature edge, we're able to track that this edge has formed and then enforce contact there. So that's the goal of dynamic feature edges. We want the best of both worlds. We want to be able to be as fast as we possibly can and as robust as we possibly can. Right? So our goal ultimately is to reduce that extra runtime to the point where we can make dynamic feature edges the default. And this is where we are. If this and here we're looking at a very large, so more realistic model, 29 million degree of freedom car crash model. With the default feature perimeter edges is like 286,000 edges. Our previous implementation of evolving feature edges delivered this performance here. So you can see we said earlier about 50% more. And now we've improved that considerably. Still not quite there. The red line represents our threshold, which we've decided is about 15% above the runtime for perimeter edges only, which we think is a good balance between running this the first time only to discover that you got bad results, and then you have to run it again with feature edges turned on. So it's 15% or run it twice typically. So that's our threshold there. Another enhancement is the introduction of a cyclic symmetry constraint in Abaqus explicit. So we've had cyclic symmetry constraints in standard for many years, and this is particularly useful for those situations where you may be complicated geometries, in particular where you don't have matched meshes on the symmetry planes, and it becomes quite difficult to implement that constraint. So the interface very similar to what we have in Abaqus standard in terms of the keywords and so forth. And this is just an example. Here we've got 3 different parts. It's kind of concentric rings, and then the cyclic symmetry constraint is being applied. And here we're looking at the deformations on those boundaries. So what we want to see here is that any deformation applied at a point on one boundary is mirrored, if you will, at the other boundary. So it's a verification example of that capability. Another enhancement, if you will, is some updating of terminologies. For many years, really since the beginning, when talking about contact or constraints, there was a master-slave terminology. And I'm sure, and as many of you know, those types of terms are becoming less acceptable. So we had a company-wide initiative to replace this terminology with something that is more compatible with our current mainstream usage. So what we've done is mapped the master term into main and the slave term into secondary. So these are the new terminologies that we'll be using going forward to represent nodes basically on both sides of a constraint or a contact interface. The previous terminology is still there, will remain there for backwards compatibility purposes for some time, but everybody is encouraged to start adopting the new terminology as soon as possible. Another output enhancement here has to do with automatic selection of element status output. So element status basically tells us if an element has failed or not. This applies to both standard or explicit, and this is used by Results Explorer and Abaqus Viewer to remove failed elements from the mesh plots. This was not activated by default, so if users forgot to turn on status for their simulations that had element failure, you would get a plot like this and wonder what is going on and be a little upset because you don't have the output you need to get the right plot. Whereas today, now it's selected by default. You don't have to remember to turn it on, and you're going to get an animation that looks more like exactly what you expected. I think this is the last one that's primarily focused on explicit, is the introduction of distortion control for C3D10 element. If you recall, we recently introduced the C3D10 second order element in explicit as an alternative to the C3D10M that existed for many years. We're looking for the C3D10N to fully replace the 10M version going forward. One of the missing features, if you will, with C3D10N was the distortion control. So this is really intended for those simulations with extreme deformation, where elements can potentially flatten out or even invert. Obviously, when an element inverts, then that's it. The simulation's done, gets kicked off the machine or something like that. Floating point errors, etc. When really you really want it to keep going. You're not interested in the results at that specific element. Obviously, but we want to keep the simulation running. So distortion control has been introduced for C3D10, and this is an example of crush test. You can see here, I think, a pretty good example of the how extreme the deformation can be. On the right side, we have the analysis without distortion control. It fails, you can see, before completing the step time, whereas with distortion control, we're able to keep this thing on the machine and complete the simulation. Okay, switching gears now to enhancements that are primarily focused on Abaqus standard. The first is introduction of coupled temperature displacement XFEM. So if you recall, XFEM is a method for modeling crack propagation through a mesh, where the crack boundary doesn't necessarily correspond to an element boundary. That's kind of shown in the cartoon here. We have a single element, and we're able to propagate a crack through that element without having to have a mesh that knows a priori where that crack might occur. Up until now, XFEM was supported only for structural displacement degree of freedom simulations. We've now extended the XFEM implementation to include heat transfer, including thermal conductance and so forth, and radiation, whatever, across the evolving crack interface. So as the crack forms, surfaces are exposed, you can capture thermal effects across those interfaces, in addition to structural effects like friction and so forth, which have been available for several releases now with XFEM. So this is particularly useful for those applications where the cracking is driven by typically extreme thermal cycling. And there's an example here on the screen here of, you can see some cracks that are forming due to the thermal effects that are applied to this component. Another enhancement is the introduction of the material parameter for beam general section. There's several beam-related enhancements coming up here in this release that I'll talk about over the next couple slides. So previously, beam general section, you specified material properties directly on the data lines of the beam section keyword, which is fine, although we discovered that it's not consistent with what we do for shell general section, where you can specify materials, and it turns out it's just more convenient sometimes, especially for companies that have material libraries and so forth, to be able to just keep the materials in a separate library and specify them and reuse them as needed. So that's basically what this enhancement is all about. You can now specify the materials directly and then reuse them. Both syntaxes are still accepted, although this becomes the preferred syntax going forward. Another enhancement related to beams is the introduction of some new cross-section types here, a channel section, I should say, and then a hat section. These enhancements were driven primarily by customers in the aerospace industry, but I think have application across many different industries, including structural, civil, ship, and others. Another enhancement that is related to the use of beam models is related to meshed composite cross sections. So here, composite doesn't necessarily mean composites in the typical sense of laminates and so forth. It could mean just different types of materials. An example here of maybe a steel steel outer thing with foam inside, or fluid, or whatever it is. So composite in a more general sense here. So, you know, and if you imagine a cross section like this extruded out of your screen, you know, to a significant distance, there's a desire when you have components like this, especially when we're talking about optimization algorithms, to abstract this into an equivalent beam property. And we can do that. It's by meshing this 2D cross section, computing the equivalent beam properties, and then applying this matrix, the resulting stiffness matrix, to a beam using beam general section. So we've had a capability to do mesh composite cross sections in Abaqus for a number of years. However, they were limited, in particular the ability to capture the effects of in-plane warping, which can play a significant role for many of these beam structures. So what we've done is extended the mesh composite section library to include some new element types that include these additional warping degrees of freedom. And just a quick example of a typical application. Here we're looking at a blade, a rotor blade, maybe of a helicopter or a wind turbine or whatever. It's got some varying cross sections. We generate the cross section properties using the beam section generate. We get a lower dimensional model beam representation here. This work was done in collaboration with some customers and our partners in SimPack, the multi-body simulation software that we provide. So we can import these beam properties into a multi-body simulation, compute the the loads and so forth, and then recover, resulting from the dynamics, and then recover the stress deformation inside the rotors. And obviously the outside of this can be driven by an optimization typically. Today, these matrices that are generated as a result of the warping are dense, so unfortunately at the moment we can't run them with the Abaqus beam general section, but that's an enhancement that's currently in progress, is enhancing the beam general section so that we can use these dense matrices from the mesh composite sections directly in Abaqus as well. A couple enhancements related to materials, and there's really a whole bunch this release. I'm just going to pick two right here. First is the introduction of a new damage initiation criteria called the LARCO5. This is for polymer matrix composites, fiber reinforced composites. It was available for a couple years as a subroutine, now fully integrated into Abaqus standard. Supports three-dimensional plane stress, shell, solid elements, and so forth, and also works with the enriched regions of an XFEM simulation. So this is just an example, a validation example that we put together using the new damage initiation criteria with an XFEM simulation. So the fibers oriented, the primary directions, principal directions have different orientations in these three examples. Another enhancement to damage initiation is a new criteria for ductile metals, so-called Hosford-Coulomb interface. You can see it's damage initiation, can be used with various types of plasticity models, Mises, Johnson-Cook, et cetera, and as is true for pretty much all of our different damage criteria, they can be specified independently. Whichever one triggers first signals the onset of damage, and then you can optionally include damage evolution to actually capture the failure and evolution of that failure. This is an example here of a benchmark example of a specimen in tension to assess the implementation of this damage initiation criteria. This is a picture of the test specimen here, and we're comparing the simulation results, the solid lines, with the published benchmarks, and you can see quite nice agreement between our simulation and the published test data. And this is available in standard explicit, and the curve here is showing that we get basically the same results no matter if you use standard or explicit. All right, so the next couple slides, I'd like to just review linear functionality in Abaqus. Abaqus is typically looked at as the code that you want to use for the most challenging nonlinear problems. and maybe not looked at as much as a go-to solution for linear functionality. And we don't think that's right because over the last 10 years or so, we've basically re-implemented the entire scope of linear functionality in Abaqus from the ground up. It's always existed. Most of these things have existed for quite a few years, but they were limited in terms of modern, mainstream, large-scale linear dynamics. So all of these procedures and things have essentially been re-implemented on top of a high-performance database, and based on high-performance solvers, in particular the AMS eigensolver. So I'm not going to read through the whole list here, but this is a pretty complete list of the capabilities and the different procedures, dynamics, and linear statics that are available today in Abaqus. And as I said, one of the key technology underpinnings is high-performance solvers, including the ability to leverage GPUs for things like steady-state dynamics and AMS eigenvalue extraction. And what we find is that we've been so successful speeding up the solver parts of these simulations that other parts of the simulation are starting to rear their heads as performance bottlenecks, and in particular, the generation of results, which in the case of linear and especially mode-based, requires a little more expensive recovery process to get those results back from the mode-based solution. So this is a couple examples here to show this effect. So the blue bars in this case represent the total time it takes Abaqus standard to solve a problem. We've got two examples here. One is a linear static with 100 load cases. It's a big model, 24 million degrees of freedom, so fairly sizable. And then another is extraction of eigenmodes, so 100 eigenmodes from the same 24 million degree of freedom problem. What you can see is that the recovery of the results was a half or more of the total solution time, and this is because, and remember the rest of this time here is for the solver, and in this particular example we're running on a 40-core machine, so if we were just running this thing scalar, this would, instead of being 3,000, it would probably be 60,000 or something like that, and this number becomes not that big. But as we speed up the solver part, this number becomes significant relative to the total runtime. So what we've done is gone in and taken a very deep look at the scaling and performance of the element output routines, and what you can see here is the first results of that, pretty significant improvements in element output. Reductions in element output times for these common linear workflows. Another limitation that has primarily shown up for the linear dynamics procedures is there was a limit of 16 million nodes in the model on a single compute node. So if we run on a single compute node that maybe has, I don't know, 12 or whatever cores, so we're running in parallel, but it's still on a single compute node, there was this limit of 16 million nodes, which wasn't such a big deal for procedures that supported DMP. We could scale off across multiple machines, and then as long as there was no more than 16 million nodes on a single compute node, then you're fine. But it turns out that the linear procedures, eigenvalue, cannot run in DMP mode, at least not yet. So this limitation was becoming a problem. So we've removed it essentially. So now we can run these larger problems, large-scale linear problems on a single compute node, even when there's more than 16 million nodes in the model. And then another performance-related enhancement is related to Abaqus Explicit. So here, and we've talked about this a little bit in the past, it was under development, but it's now something that is part of the release, is this idea of hybrid message parallel and explicit, which is essentially the combination of DMP, so running multiple processes and then communicating between those processes using message passing interface, and then threads or SMP, where information is communicated between parallel domains by sharing memory. Right. So the original implementation was DMP, and that's basically shown on the right here, on the left, I should say, where here is an example of a single compute node with 16 cores, and another one with 16 cores. So we've got 32 instances of explicit.exe running total, and they're all communicating with each other via MPI. That was the original implementation that dates back to the days when a compute node didn't have 16 cores. It had 1 core or 2 cores or something like that. Now the trend in the hardware is multi-core compute nodes sharing memory. So, and what we've discovered is that there is some overhead associated with the communications of MPI. We can improve performance by having a single explicit process on a compute node or a socket, and then the communication is done through shared memory within that compute node. So that's what hybrid message is all about, is extracting the best performance we can out of the current hardware architectures. So there's an interface for this now. CPUs equals N tells basically how many threads or how many cores we're going to run on. And by default, there's also the number of domains that the model will be split into. And now there's an additional parameters that says how many threads per process. So we can do a little math there and determine how many MPI processes and then M threads per MPI process. Typical performance gains are in the range of 10 to 40% right now. It depends on the model and so forth and the hardware, and we expect to see this continue to improve. Right now, the default remains DMP, so if you want to make use of this capability and explore it for your particular models, this is the interface you use to do so. Okay, so that's the survey of what's new in Abaqus 2021. As I mentioned earlier, it's really just a selection. There's literally dozens more of enhancements in the release, so if you want to know the complete story, as always, refer to the release notes. So I'd like to spend the last few minutes talking about 2 very interesting new applications that we've developed. And the first is related to material calibration. So Abaqus provides a very general purpose material library, in the sense that we have behaviors that can be combined in very specialized ways. So take elasticity with viscoelasticity and plasticity. You can combine those in various different ways to achieve very complicated behaviors, which is great. The challenge is that when you get test data for a material that exhibits those types of behaviors, you somehow got to convert that into the parameters of the specific constitutive models that are available in Abaqus, which is a challenge. Until now, really relegated to experts or consulting laboratories and so forth, and using customized scripts and one-off optimization algorithms and so forth. What we've done is developed a new application focused on Abaqus to enable calibration of material models. Right. So in a nutshell, what we do is we take physical test data, which you can then massage, decimate, smooth, whatever inside the application, construct a replication of the actual test itself, so a numerical representation of the physical test, take a guess at some initial material parameters, and then run that inside an optimization loop such that the output of the optimization is some calibrated material parameters that you can then use in a downstream simulation. So this is a screenshot of the application itself right here, and you can see a very broad coverage of the material models in Abaqus. The feedback from our customers who have tried this has been overwhelmingly possible. Fairly easy to use. A lot of the knowledge that you need to do calibrations is built inside of this application, and it's also available on cloud, so fairly easy to get your hands on. We can set up, contact your local sales representative, and we can set you up with a license to access this application via cloud very, very quickly. Just a sneak peek ahead on where we're going, future direction. So currently primarily focused on constitutive models, materials that are built into Abaqus. But there's other areas where calibration or these same types of approaches make sense. For example, if we're going to calibrate idealization. So here's one example where we're modeling a spot weld, which we can do in 3D and be very, very accurate, reasonably accurate if modeling this spot weld in 3D, and failure of that. But for system level models, you oftentimes want a simplified representation. So I want to represent this complicated spot weld and all of its all the glory of its physics with a beam representation or a connector, if you will. So calibrate this, run it through the sequence of load scenarios, and then output some parameters so that we can replicate that behavior with a simplified, or at least more computationally, efficient representation for large-scale simulation. So that's a little peek ahead to the future direction of the material calibration app. And then the last topic I wanted to talk about here today is something that we're really very excited about, is an application we call Simulation Manager, which is a browser-based interface for running Abaqus jobs and managing Abaqus data on the cloud. So you can see a screenshot of the application here. It's web-based, so this is inside of a browser. Our current implementation, which is out there and available now, we have three different compute configurations available. We call them small, 18 cores, medium, 36, and large, 144 cores. And with our upcoming release, which I believe is going live in just a few days or so, looking to extend that to some additional compute configurations, both smaller and particular and larger. We support multiple Abaqus versions, so you can choose which Abaqus version you want to run. Default, obviously, is our current version, but you can reach back to previous versions if you choose. There's storage, high-performance storage available, and this also includes remote visualization with Physics Results Explorer, which is a 3D experience-based application. It has a client-server architecture, so you run the simulation on the cloud. There's a HP Viz engine, if you will, that runs on the cloud, does all the heavy lifting, runs in parallel, and so forth, and that communicates with a client, local client installed on your machine, where you actually see the user interface and interact with the model and so forth. And then last, and certainly not least, is we have the existing token-based licensing model, which I'm sure most, if not all of you, are familiar with, and that's now augmented with a what we call credit-based compute licensing, which is more of a pay-as-you-go, pay per job, and it removes a lot of the limitations of token-based licensing. For example, for a small fixed entry cost, you're able to run on a very large 144 configuration that would require quite a few tokens to run if you will use the token model. So that's the essence of Simulation Manager. So what I was hoping to do right now is just take a quick view in real time of what it looks like. So this is it. It's running right now on my laptop. This is the web-based interface. You can see the on the right here, I have a listing of some jobs that I've run. Generate the little thumbnail images of these jobs and so forth. It kind of looks like we're browsing a directory structure, and you can certainly think of it and use it that way. So here's my simulation, and if I look over here, the content, lots of familiar things we're seeing here: an input file, our message files, status files, our output files. We can get access to some of the log files, so I think things like the message file, again, I think very familiar with that, the status file, all available to look at there. There's also a monitoring capability, fairly rudimentary right now, and probably most useful when we're running a simulation, so you can monitor the status. This is an area of we're looking at other ways to improve the monitoring capabilities, for example, visualizing jobs in 3D while they're running and so forth. So I mentioned before that this can be thought of as a browser for files, but it's actually much more than that, because all of these simulations are being stored as objects in a database. So there's more to it than just files. There's versioning. Which version did I run? There's dependencies between them. For example, between a global model and a submodel. My submodel knows that it depends on the global model, and there's tools to browse those types of relationships and so forth. So I'm going to take a chance here and try to create a new simulation. So just to show how easy this is. So I'm going to run a simple little flange model. So I'm going to create the simulation. That's step one. So it's going to go and create a new simulation object in my database. So that's it, done. Here's the flange. Here's my input file. It's really just as simple as drag and drop. So that was it. It's a fairly small model here. Obviously, if you have a large model, it's going to take a little more time to get that simulation up and running or transfer that data. But the good news is once it's over there, you're done because you don't have to transfer data anymore. And then we're going to run it. So this is the interface for running. You get a choice of the different types of, your license model. Use tokens or credits, depends on what you have available. You can do a data check or whatever if you want. Configuration, you can choose the cloud configuration, or by default, we're going to look and say, okay, this model is of a certain size, and do an estimate of what is the most efficient configuration to run on. You can choose the Abaqus version, like I said. So the default is the most recent version. So this is the 2021X Hotfix 3 that we're running on the cloud. We got different output options. This may be new to some of you. We have the ODB, which I'm sure everybody's familiar with, but we have a new format. We call it SIM, which is the format used by 3D Experience Results Explorer. So it's a more high performance output database that we use for Results Explorer. So I'm going to turn off the ODB for this particular simulation and focus only on STEM and also what we call experience content. So what this is when the simulation is finished, we're going to generate some lightweight results that can be used for visualization on devices that can't, like mobile devices and so forth. And it's also used to generate these icons that you see here. To help you know what's in your simulation. That's pretty much it. Click run and we're up and running. You're going to see it submitting to the job. Takes a few seconds. So what's happening now is out there in the cloud, we've spun up an instance of on an HPC cluster, found the input file over to there, and it starts up and running. We can look at the files. So this is the log file, so you can see it's checking out licenses, and we're running batch pre right now and so forth. We'll get through there fairly quickly for this model into standards. Now we're going to start seeing some of the other files that we're familiar with, message file and so forth running. So this is a fairly small job. It's going to run fairly quickly and be finished. And then the last feature I just wanted to quickly to show here was visualization. So once the job is done, we can open it, and here in Physics Results Explorer or 3D Play, which is a lightweight visualization tool. So that's all included as part of this package, and I brought it up. It takes a few minutes to bring up typically, depending on your connection and so forth. So this is just a quick view, a quick look at the bushing model that I'd run previously in the application on the cloud. So this is the client application running locally on this workstation, and then the result HP Viz engine running remotely on the cloud. And just maybe a quick overview here. All the tools that you normally used to, the ability to look at different time steps, create animations, view cuts, you name it, XY plots, all that kind of functionality is available in Results Explorer. So that's pretty much it for this presentation. Just to wrap up here briefly. Two key takeaways. First is development of Abaqus structural simulation to address high-value workflows continues at a rapid pace. I think there's more more new features in 2021 than I can remember really for many years. So really lots new there. And as I mentioned, take a look at the release notes for a complete listing of everything. And then second, some new applications that we're developing based on 3D experience that share a common user interface, underlying data model that provide access to cloud computing, which is very easy to use and significantly increased user productivity. So we're very excited about all of these new developments and hope you are too. So with that, I'd like to thank you for your attention.